All right, today we're going to talk about simplifying radicals. Um, so a radical is any expression um, underneath the square root sign, right? So um, we can have the square root sign, and we can have an expression under there. It can be a number, it can be an algebraic expression, and we call this number underneath. We call this the radicand. Okay. And it doesn't even have to be square roots. It could be cubed roots or fourth roots. But today we're just going to talk about square roots because that um, is going to be most useful for us when we start talking about the Pythagorean theorem. So a few properties of radicals that we need to remember um, are, so some properties of radicals are first that if you take the square root of a product. So let's do A times B. If you take the square root of a product, that is just equal to the product of each of those square roots. Okay, so we can split that product by taking the square root of each of those things. And similarly, it works the same for division as well. If we take the square root of a quotient, so square root of a divided by b, that is just equal to the square root of a divided by the square root of b. Okay, so those are two properties that are going to be useful for us. It should be, we should note this. So note, it is not true. Okay. So this property doesn't extend to sums and differences. So for example, the square root of a plus b is not equivalent to the square root of a plus the square root of b. Okay, that's not true. And it works the same with subtraction, right? The square root of a minus b is not equivalent to square root of a minus square root of b. Okay, so this only works for products and quotients. Okay. And so what we want to do is we want to simplify radicals, and a radical is in simplest form it's in simplest form when the radicand, so that's what's underneath the square root, has no perfect square factors no perfect square factors. Okay, and what do I mean by perfect square? So a perfect square is just a number whose square root is an integer. Okay. So a a whole number, a positive whole number, positive or negative whole number. But in our case, we're going to be dealing with positive numbers. Okay. Um, so let's look at some examples here. Okay. So let's do some examples of simplifying some square roots. So obviously um, we can have something like the square root of 36. Okay, and so we all happen to know that 6 times 6 is 36. So the square root of 36 is just 6. So we can simplify that as an integer. Okay, so that's an easy case. So if it's ever a perfect square, okay, so this tells us that 36 is a perfect square. If we ever have a perfect square, we can just simplify it to its integer form. Okay, but let's look at an example like the square root of 20. And so we have to think, well, okay, how do we get perfect square? How do we find out if 20 has any perfect square factors? Well, the easiest thing to do is to factor the radical. So we know that uh, 20 is square root of 4 times 5, because 4 times 5 is 20. And then using our property uh, from above, right? Our property here, okay? The square root of 4 times 5 is just equivalent to the square root of 4 times the square root of 5. And since 4 is a perfect square, the square root of 4 is just 2. And so we're left with 2 radical 5. Okay. And we know 5 doesn't contain any perfect squares because 5 is a prime number. Okay. So it has no other factors other than 1 and itself. So this is the simplified form of square root of 20. And this is the simplified form of square root of 6. So notice that if you were to go into your calculator and put in square root of 20 and then 2 times the square root of 5, you would get the same decimal approximation for both of these. Okay, so they are equivalent numbers, but this is just a simplified form of that. Okay, let's look at another example. Um, so how about the square root of 28? And again, if it's something, a relatively small number, and you know that there are some perfect square factors in there, so 4 is a perfect square, for instance. So we know square root of 28 is 4 times 7. So square root of 28 is equal to the square root of 4 times 7, which is equal to the square root of 4 times the square root of 7. And the square root of 4 is just 2. And again, 7 is a prime number, so we can't, there are no perfect square factors in there. So it's just 2 times square root of 7. So that is the simplified form of that. Um, so now let's look at one that's maybe a little tougher. Okay. So obviously, if you can find a perfect square factor, you can factor it, and you want to find the largest perfect square factor. Sometimes it's not as easy to tell. Okay, so let's look at square root of 56. And so I don't know of any perfect squares in 56. So one thing we can do is we can draw a prime factor tree for 56. Okay, so 56 um, is divisible by 2. Okay, so if I divide it by 2, I get 28. Okay, and then of course we can already see from up from above what the factors of 28 are, but I can keep doing this. I can divide 28 by 2. Let's say I don't know the other factors of 28. So I divide it by 2 and I get 28 and 14. And I can keep going, divide 14 and I get 2 and 7. I'm going to keep going until I get prime factors. Okay, right? This is the prime factorization. Okay. So now what it's telling me is that, okay, I have 56 is equivalent to um, 2 times 2 times 2 times 7. So 2 times 2 times 2 times 7. And those are all the factors that make up 56. Okay. Well, anytime I have a pair of prime factors, okay, that means when I take the square root of that pair, I can pull one of those outside, right? So I have a pair of prime factors, okay? And 2 times 2 happens to be 4, okay? So I could write this as square root. So let's do it this way. Let's write this as the square root of, this is the square root of 2, okay? And then I've got my other two factors of 2. So I'll write those as 2 squared times 7, right? So this is 2 squared, okay? And that's where that one comes from. And then when I use my properties, well, the square root of 2 squared is just going to be 2. So I can pull that 2 out front, okay? And then what I'm left with is these other 2 factors that are left inside the radical. So I've got 2 times 7. Okay. And then of course I can use my property, and the square root of 2 times 7 is the same as square root of 2 times 14. Okay. So we can prime factor it, and anytime we have a pair of prime factors, we can pull that uh, out front, out of the radical, right? Since we have 2 2's, when I take the square root of that, I'm only going to be left with 1 2. Okay, so that's where that one comes from. Okay, so and we could have prime factored any of these previous ones as well. Okay, so if I go back, um, if I go back to square root of 20, for example, okay, so if I did square root of 20, and you say, well, let's say you don't know all the factors and you want to do the prime factor tree. So 20 is 2 times 10, and then 10 is 2 times 5, and I have a pair of 2's here, okay? So since I have a pair of them, my 2 comes out front, my 2 comes out front, and I'm left with the square root of whatever is left, okay, which is just 5. So that matches what we got previously. So the prime factor method works best, especially when you can't easily see um, a perfect square factor. Okay, and it will always work. It's a very methodical way uh, to do it. So let's look at this. Let's look at 8 times the square root of 24. And so let's try to simplify this. Well, we don't have to worry about the 8 right now, but let's tackle the 24. Okay, so I'm going to factor the 24. That's 2 and 12. Okay, and then I'll divide that by 2 again. So that's 2 and 6. And I'll divide that by 2 again, and that's 2 and 3. And so you'll notice I've got a pair pair of 2's, okay? And then these pieces right here don't have any matches, so they have to stay underneath the radical, okay? So what I have is I've got my original 8, and then I've got the 2, okay, which comes from these pair of 2's. So when I square root that pair, I'm just left with 1, 2, square root, and then these two things, the 2 and the 3 that don't have matches, they have to stay underneath the radical. So I'll write those in red. So I've got 2 times 3. Okay. And so when I simplify this all, I just multiply my two numbers outside of the radical. 8 times 2 is 16. And my two numbers inside of the radical, 2 times 3 is 6. And so here is my simplified radical. Okay. We'll do one more example, and then I'll let you get started with some practice. Okay. So we've got we've got 6 times the square root of 150. Okay. And again, I will use my prime factor method. So I'll come over here. And let's see, well, I know right away this is divisible by 10. Okay, so 10 and 15. And so now let's divide up 10. So 10 is 2 and 5. And those are both prime numbers. And 15 is 3 and 5. So those are both prime numbers. And I can see that I have a pair of 5's. Okay, so those are going to be able to come outside of the square root. Okay, when I take the square root of 5 times 5, that's just going to leave me with 5. But 2 and 3 don't have matches, so they're going to have to stay underneath the radical. So I've got my original 6, and then again from my pair of 5, since I have a pair, I can bring one of them outside the radical. And then I'm left with the 2 and the 3 underneath the radical. And so now I can multiply the numbers outside the radical. So I get 30, and then multiply the numbers underneath the radical. So I get 6. So I get 30 times the square root of 6. Okay. So that is how you simplify radicals. And so now posted for you on IXL is this exercise on simplifying radical expressions. And there's the 3-digit code for that. But you can work on that for the remainder of class and try to finish that up for homework. All right. I'll talk to you guys later.